So, what we have been looking at in the last class, if I recall correctly, is the following. Okay. So, so the problem or the objective we had was that we were looking at still the vertex cover problem, but we call it if of guarantee or I don't know, if of guarantee vertex cover, and the guarantee was f of LP. Okay. So input was G K and my parameter was K minus LP value for the vertex cover of G. The question was, does G has a vertex cover of size at most K? VC size at most K. So we still were looking for a vertex cover of size at most K, but our parameter or the way we wanted to measure the running time was different. Okay. So last time we discussed several potential algorithms for this, or rather one potential algorithm, which was based on the following simple combinatorial fact. What was that? That lemma that we proved that there exists an LP opt solution to VC such that each value is in 0, half, 1. That is what we call half integral solution. Okay. Right? So this was the key objective on which our algorithm was supposed to be built. And then the second fact that we had was that we can find a LP solution where all half, or we can find an LP solution where all half is the unique solution. Okay. Right? Our algorithm was very simple. Our algorithm was very, very simple. What did the algorithm did? Our algorithm was this, simply was this. Some base cases. Okay. And then if we had some base cases and we said, pick an edge UV in my graph and recursively find solution in G minus U, K minus 1, or right? And if any of them return yes, return yes, right? So this was our base algorithm. So we had some base cases, and which we will discuss today. What are those base cases? Okay, and okay, and so our algorithm was fairly simple. So what was this? So so one thing to ensure was that what was our base case? Our base case was, what is base case for us? That when you're measured, which is like K minus LP, this is mu is less than or equal to 0. What do we know? We can't further branch. Right? Which means this case should be handled in polyton. Right? So, and but if you notice, what is this tells us? This is a very interesting thing. Okay, this is a very interesting thing. Okay, basically, what I'm saying, I mean, it means our algorithm has inbuilt an algorithm which, given G, what it can do, which given G can test whether ILP equal to LP in P time, right? Meaning, is the integral solution to G equal to the LP relaxation, right? If we just wanted to do that, we can do that testing in polytime, okay? And how did this algorithm work? If you recall, the way this algorithm works is fairly simple. So basically what happens is that, okay, so suppose, like we can test, suppose what is the meaning that ILP equal to LP? It means I have a vertex cover S, okay, and the cardinality of size is equal to LP solution, right? This is what it is, right? What is the meaning of this? So there is a solution that assigns 1 to these vertices and 0 to everybody else, right? And the value of this, so what is it? This is an integer, like this is a solution, this is an integral solution to our vertex curve problem. And what is the property? The property is that there exists a solution, okay? There exists, and what the property that the size of the solution is equal to the LP value, right? So if this is the case, then basically the way we design our algorithm was fairly simple. If this is the case, can all half be unique solution here? Please tell me. Right? Suppose we had an algorithm which, given a graph G, can test whether all half is a unique solution to its LP, right? So now we do have an LP solution which is literally integral. So definitely when we will apply this test, what will happen to this test? It will fail. Am I right? Is this fine with all of you people?
Yes.
Okay. So what I'm saying, so suppose you have an oracle, okay? Suppose you have an algorithm. What is this? Test whether all half is unique solution. Suppose this is an algorithm. Now, what is the property of this instance? This instance is a property that there is an ILP solution, integral solution, whose value is equal to the linear programming. Now, if we give such a G, what I'm going to get returned? I'm going to get no, this is all half is not a unique solution. And you're going to get an LP with some zeros, some halves, and some ones. Am I right? Now, and we know that this is non-zero, like number of zero entry is non-zero, number of but then we have a reduction rule. What is the reduction rule? What happens to this reduction rule? Right? The reduction rule was, if you recall correctly, is that G minus all the vertices which gets value 0, union all the vertices which gets value 1, right? And what is my parameter change? Is this. Is that fine? So this is what we did. Is that okay?
Yes.
Okay. So what is the meaning? Okay. So this is what we perform. And what is the property of this? That we always know there exists an optimum solution containing these all ones. It means if I remove this, what happens? So imagine that we have LP solution containing whose LP solution equal to some ILP solution. Okay. And now we have what is the when we apply this reduction, what is the property? There exists an optimal solution S that contains V1. Am I right? We know this property. What is the meaning of that? The meaning is that this size of S is also equal to ILP, and which is also equal to LP, right? So now, right? So what is this? So now S minus V equal to 1 is an optimal solution to what? G minus V0 union V half. All I'm trying to tell you that once you delete these vertices which have been assigned 1, the property that LP is equal to ILP in the reduced instance is maintained. Okay, so what is maintained because of this reduction? So what I'm trying to say that G has LP equal to ILP if and only if G minus V0 union V half has LP equal to ILP, right? So because of this equivalence, what will happen? We will keep applying this reduction rule, right? And because every time we are maintaining the fact that look, LP equal to ILP, LP equal to ILP, what will happen eventually, right? Eventually happen that we will always fail. And when you fail always, you are always maintaining you are making a progress because you are able to remove some vertices from your graph. So after polynomially many steps, if you are not able to get that all half is the unique solution, what happens? You are able to get that LP equal to ILP and you are done. Right? So this is why this testing whether all have a unique solution or not is also can be used to test whether graph has LP equal to ILP or not. So that's one thing that I wanted to tell last time, which we did discuss, but I wanted to give you why. Okay. So is this clear now that we can test whether LP equal to ILP in P time? Is this fine?
Yes.
Okay. Basically, what will happen that if LP equal to ILP, right? So, you know, I have not told you, right? There are some base cases, right? Right? Here, base cases. I want to test, like I want to solve if mu is less than equal to 0. I want to test something in poly time. Okay, do this. Okay. Now, before I branch, okay, before I even branch, okay, first what I branch only when all half is a unique solution. Else, what I do, I apply reduction rule. Okay. So what is the reduction rule? Reduction rule is simple. You have V0, V half, and V equal to 1 as LP solution. Right? Now, we know that this is Z, comma K is a yes instance if and only if G minus V equal to 0 union V half, or rather, why write this? Write graph induced on V half, K minus 1 is a yes. This we know. This we have already proved. Now, as I told you that when we are applying reduction rule, it is important to check that measure does not increase. Right? It could decrease, it could remain the same. That's perfectly fine. So we have to test this. So what is the measure of the left-hand side? So left-hand side measure is what is this? K minus LP of G. Okay. And what is the measure of, let's call this graph G prime one. Is that fine? Is this fine? Okay, not okay.
Yes.
Right? So this is a measure associated with the graph G, which is K minus the LP value of LP solution. And what is the mu of G prime is K minus it. So correctness, there is no issue. We have already proved it. But we have to also show that our measure does not increase when we have applied this reduction rule. So what we have to show? Mu of G prime is greater than or equal to 0. Right? Then I know that Measure has only decreased, it has not increased, right? Or in other words, mu of G prime is less than equal to mu of G, right? What does this imply? That mu of G prime is less than equal to mu of G. Okay, so let's try to prove that. It's very simple. K minus LPG minus K minus V equal to 1 minus LP of G prime. Is that fine? So now K minus LP of G minus K plus V equal to 1 plus LP of G prime. So K gets cancelled. What is this? Now it is V equal to 1 plus LP of G prime minus LP of G. Is this fine?
Yes.
Okay. And now what we have to show that this is greater than equal to 0. And when will that happen? If this quantity is greater than this quantity, right? What I want to show that this is greater than equal to 0, right? To do that, we need to have the fact that V greater than equal to 1 plus LP of G prime is greater than equal to LP of G, right? Is that okay? Is the claim okay? That this is what I need to show. Okay. But is this not obvious? Why? Because suppose V equal to 1 plus LP of G prime is strictly less than LP of G, then let's see what we can do. Now, what is G prime? So let's draw our picture. Here was V equal to 0. Here was V equal to 1. And here was V equal to half. Like this is how. Now, and this is what our G prime is. Okay. Now, suppose LP, this quantity plus this quantity is strictly less than LPG. Suppose. Then what happens? What is the meaning of this? Let's try to understand. Okay, so now what I'm going to do, this is my G, right? Okay, assign these vertices values according to LP of G prime. And what should I assign these guys? Assign 1. Now I claim to you that every edge is covered in G. Is that fine? Look at
the claim.
Claim is that I want to show that if V equal to 1 plus LP of G prime is strictly less than LP of G, then we can obtain an LP solution for G which is strictly less than LPG of contradiction. If this happens, then we can obtain a LP solution for G which value will be much smaller. Okay, how? I said, okay, look at this is how my graph G look like. Partition into V equal to 0, V equal to 1, and V equal to half. For every vertex here, I assign the values according to LP solution of G prime. Is that fine? Is that okay? I know, imagine that this plus this is less than equal to it. So I'm saying, okay, all these guys have been assigned values according to LP solution given by of G prime. Is that okay, Sani? I don't know what they are, but this is how. But what is that ensure? That ensures that look at any edge here, right? They are satisfied in the sense if I look at their value, they're greater than equal to 1. Okay. Now, what did I do? In G, I assigned every vertex in V equal to 1 as 1. Now, look at any cross edges. What is their value?
Greater than 1.
Yeah. What is the value here? Greater than equal to 1. What is the value here? Right? But what is the value here of an edge?
There is no edge.
There is no, but there is no edge. Which means this new assignment that I have done, right? It's a feasible assignment. Is that okay? Is that fine with everybody? That
Yes.
that new assignment is a feasible assignment. Okay. And what is its value? Its value is LP of G prime plus V equal to 1. And by our assumption, this is less than equal to LP of G prime, LP of G. Right? What happened now? A contradiction. Right? Which implies that we always have that LP of G prime plus V equal to 1 is greater than equal to LP of G, which implies that this implies mu of G prime is less than equal to mu of G. Is that fine with everybody? Right? I cannot ensure that measure strictly decreases. Look at this. This every time you apply a reduction rule, every time you apply this reduction rule, right? Solution size always decreases. Is that fine with everybody? That whenever I apply this reduction rule, then the size of the solution always decreases. Is that okay? Because when are you applying this reduction rule? It means you are at least putting some vertices in your solution and reducing your budget by something. Is that okay? So solution size decreases. Okay. Okay. But my measure in this case may not decrease. It could just remain the same. Because what is a measure? It's a difference between my solution size and my LP value. That difference may not strictly decrease. Solution size decreases, but my new measure may not decrease. Like when I say may not strictly decrease, it does not increase. That is what our proof told us. But it could also happen that it could remain same. Okay. So this is something important point to note. So this is the very basic difference between when we are parameterizing by solution size and the difference, right? When we are parameterizing by solution size, whenever we apply such kind of non-trivial reduction rule, the size of the solution strictly decreases, and hence in those cases, our measure decreases, and we use this to design our branching algorithm very nicely. Remember when we said, oh, if look at the degree 2 reduction rule, right? When this happens, then I'm sure that we have to apply one more thing and k will drop by 2, and we utilize that in our algorithm. But here we cannot utilize any of those things. Okay, why? Because the difference may just remain the same. Okay, so is this message and idea clear to all of you?
Yes.
Okay. Okay, so that's nice. Okay, so what we have been able to show? So we have showed that in our algorithm. Okay, so this is something which you have to be always worried about these things. Right? So we have shown that base case can be solved in t time. Okay. Secondly, we also saw that reduction rule does not increase my measure or potential slash potential. Okay. Right? So when we are going to branch, right? What is the property of G? What is the property of G? That we have that for LP of G, all half is the unique solution. Is that fine? So when we are planning to branch, we know that all half is the unique solution, because if it was not, we would have rejected it, and that would have meant applying a reduction rule. We would have applied that reduction rule and our measure would not have increased. So that's great. So when we are really trying to branch, we know that all half is a unique solution. Okay. And now, what did Bay say? Because all half is the integral solution. Now imagine U and V is an edge now of this graph G. Okay. Now, what was our first branch? We said, okay, it's simple. It's look for this, right? This is what we did, right? Of course. So the only branching step of our algorithm is this one. Okay. Okay. And now we needed to say that our measure drops by at least something in each of the branches, because then I know that the branching factor is 2. So if we are able to bound the depth of our tree by some function of our measure, then that will imply an FPT algorithm in our measure. Okay. So how did we say? Okay, we said, okay, fine. That's okay. Look at this. Okay. So let's call this G prime. And we said, look at LP of G. So what is LP of G? Is basically equal to n over 2. Do you agree? It's exactly equal to n, because all half is the unique solution. We just now said, and if n is the number of vertices. Now, we said, okay, look at LP of G prime. Okay. LP of G, look, if I put every vertex half, right? If I put every vertex half, that's definitely a feasible solution. So LP of G prime is going to be less than equal to n minus 1 by 2. Is that okay? Okay. But we know that LP solutions are integral. So what are potential? So I know that LP of G prime is an element of n minus 1 by 2. Right? Is that fine? N by 2 minus 1. Right? Because n by 2 minus 3 by 2 and dot, dot, dot. Is that okay? Because it is an integral solution, right? Because it's a half integral solution. It's a multiple of half. So we said, so how did we argue? We said, look, first let's make sure that these are not, like these do not happen. Let's make sure that these cannot happen. Okay. Let's make sure that these cannot happen. Why? Because we want to say, if this happens, we can do something interesting. Okay. Why? So I said, look, if this happens, what is the graph? This is your U and this is your G minus U. Right. So if these guys has value, say here, but say its value, LP value is say less than equal to n by 2 minus 1. Okay. Then what can I get an LP? What kind of LP solution I can get? Well, then I can assign. What should I assign this?
Q equal to 1.
1. Then what happens?
So then original LP is not half integral.
So for sure, first of all, if this is less than equal to n by 2 minus 3 by 2, then it contradicts the fact that that contradicts the fact that n by 2 was the value of LP. So this is definitely not true. Okay. So this could exactly be equal to n by 2 minus. But if it is n by 2 minus 1, then I will assign U equal to 1. And what does it contradict now? It contradicts the fact. So now look at the value is n by 2. But what does it contradict? That all half is the unique solution. Is that fine? So even this is not possible. So what is possible then? Right? We just now concluded that all these values are not possible. So this implies LP of G prime is actually is this. Okay? So now right? Is that okay? Which is basically what is this? K minus n by 2 minus k minus minus plus 1 minus minus plus. Is that fine? So my measure drops by half in both. So what is my running time of this algorithm? So the running time of this algorithm is T mu is 2 times T mu minus half. Okay. And this is 4 to the power mu, which is that okay? Which implies that we have given an algorithm with this much of time. Okay, so is the algorithm clear to everybody? If not, please ask question, because before we go further, it's important to understand this. Is that okay? Okay, excellent. Okay. Okay, so there are ways to improve this algorithm. Okay. There are ways to improve this algorithm. So probably I can teach you. Okay. So this was a real, this was an this is an algorithm which was known, but with slight, imagine yourself that. So currently, what is the branching factor basically? So branching factor is half comma half. Okay. Now imagine if we could make branching factor as half comma 1, what can we say? Then what will the running time of this algorithm?
So T of mu minus half plus T of mu minus 1.
Yeah. So what does that corresponds to? What will this lead to? What's the number? Let's see if anybody got the numbers. Come on, this is just a recurrence, guys. Please. All of you are in front of your laptop because you're at least listening to my talk. I believe that much. It's a nice number. Okay, so let me, I think this is fun. I think. Okay. Okay, let's see. Right? So this is what? X. Yeah. This is what? X half plus 1, right? Is that okay? If I divide by x to the power mu minus 1 everywhere. Is that okay? So if I put x half equal to y, then what is this? Y square equal to y plus 1. What is this recurrence? Please. This recurrence, you have seen it several times. Isn't this golden ratio?
Golden ratio?
Yes. So this is 1.618. Okay. So y is like 1.61. So what is x? Is y square, right? So what will be this? I think, and I don't know why, but this is what it comes. Is that fine? Is that okay?
Yes.
I mean, okay, fine. Even if it is not okay, this is just some number computation which you are good at. Somehow, I really felt very nice when I saw first time that 1.6108 whole square is just 2.618. Maybe not everybody. I think so. Like, this is what I remember. Yeah. It is like something like that. Yeah. Okay. Any. Okay. Okay. So this is what we like to achieve. Okay. So we would like to achieve these kind of recurrence. So we have this kind of recurrence, we would like to go to this. And there's a nice idea to do that. Okay. So before we go do that, suppose we have the following fact. Okay. For every independent set I, okay, neighborhood of I is greater than equal to say I plus 2. Suppose this is the property we have of my graph G. What is property? That you'll take any independent set I, then its neighborhood is at least I plus 2. Then let me ask, what is the minimum degree of this graph? Can you infer something?
At least 3.
Yeah, it is at least 3 because if you have an independent set, singletons are independent set, right? So this is 3. Good. Okay. Now suppose we had this nice feature, okay, and now we branched. Okay, so we had a G, which is a very beautiful property that for every independent set I, n of I is greater than equal to I plus 2. Okay, we will worry about how to handle such cases. But suppose we have this beautiful property, does it imply now that when we branch, remember, so now I want to branch slightly nicely, either U or its neighbors. Okay. Right? So now we know that, right? Either U belongs to solution or n of u belongs to solution. Right? Now we are in the all half unique solution case. Okay, else we'll branch, like else we'll apply reduction rule as before. Right? Now, if suppose if this is the situation, I would like to see how my LP value will change. You understand my point? Is the idea clear to everybody what we are trying to achieve? So we are talking about a very special kind of graph. What is the property of this special kind of graph? For every independent set I, okay, its neighborhood is at least 2 more than the I itself. Okay. Is that fine with everybody? Okay. So now if I branch, okay, so what is the branching? Branching is very simple. And k minus u. Okay. But now, for sure, we can show this side that my mu of g minus mu of g prime is at least half, right? In fact, equal to half. We can show this. But what about this side? Can I say something interesting here? Right? You understand my question? Right? I want to see, suppose if this is your g prime, I want to understand what is the value of mu of g and mu of g prime. If I can show this is greater than or equal to 1, I'm golden. Right? So let's try to analyze that and try to see where we can use the fact that for every independent set I, this property holds. Right? What is U? Is an independent set. So n of I is at least how much? 3. Okay. Or more. We don't know. Okay. So let's try to understand what happens. Okay. So now, what is mu of g? Mu of g is k minus LP of g. And what is mu of LP? It's k minus, suppose n of u is d. Okay, so it is how much? K minus d is my new parameter, and minus LP of g prime. And remember, what is g prime? Is basically g minus closed neighborhood of u. Is that okay with everybody? Okay. Now, what is LP of g? LP of g is basically, we know it's n by 2. And this, we will have to see what is this. Okay, we'll have to come back. Now, as before, let's write it down. LP of g prime is how much? How many vertices in fact, just to make our life easier, okay? Anyway, next reduction rules will take care of these things. Okay, let's forget it. It's fine. I think we should be fine. So what is this? It is n minus d plus 1 by 2, right? Is that okay?
Yes.
Right? So we have deleted d plus 1 vertices. So at least, at most, it can be only this. Or suppose this number is like a, then it is like a minus half, a minus 1, so on and so forth. Okay? Is that fine? Now let's try to see how much it shouldn't be. Like let's, for some stage onward, let's say if it is this much, let's just forget it. Okay? It cannot be, then we can do something nice. Okay? Here is u, here is n of u, and here is everything else. Right? And so suppose this guy's value is n by 2 minus, say, d. Okay, then what can we do? then what can we do? We can make as before
1.
as 1, and that shouldn't happen, right? Agreed? Because then all half is not an unique solution. Okay, fine. So at least this does not happen. Okay. So how much it happens? So okay, fine. So it is less or more. Yeah, little bit more. At least this much is there. Do you agree? Look, less than n by 2 minus d, it cannot be. I cannot have minus more. I cannot keep on decreasing. So I should at least have this much. You get my point? No.
Yes.
Why it is not obvious, Sani? Tell me. You just now argued, you just now agreed, right? That this is not possible. You just now said no.
This one I got. But the next
Yeah. So if it is anything less than this is not possible. So what it should be? It should be more than this, no?
something plus.
So how much should be more? Next should be at least half, right? But okay, here is a funny part, right? Okay. So let's believe that this is, say, n by 2 minus d plus some x. This is equal to, say, this, right? And x is some multiple of half. What is x? X is some multiple of half. Suppose this is this. At least this much is this. All of you people agree to me. Now let's go back and try to put these values and see what values do I need and how can we get that value. Okay. So our parameter is k minus n by 2. Next is minus k plus d. Is that fine? And k minus d, so minus k plus d minus plus, right? So is that okay? Right? So we have x. Is that okay? So if I can show that x is 1, then I'm good, no? Is that fine?
Yes.
All this, I up until now, all I know that x is at least half. But then if I just show that x equal to half, I will get nothing. Is that fine? So now somehow we have to argue that in this case, we are doing good, right? Okay, so let's try to think. Okay, let's see. Why we can say that X is at least 1. There should be some clever way of saying this. Let's see.
Circuit,
Yes.
because it's a all half solution.
Hmm.
So even if one of them is 1, like when we are subtracting, we are assuming here that if it goes below n by 2 minus d, then we could set them 1 and get a better solution, right?
Correct.
So even if we could set one of them as 1 and get better solution,
Yeah, but look at this, no? That can only happen when my LP solution has value at most n by 2 minus 2. Then I could do that. I can go and assign every vertex in NU to be 1 and make a progress.
yeah,
Okay.
yes.
Okay. So let's see.
So if x equal to half,
Hmm?
then if x equal to half,
Hmm.
then we can like assign this every vertex 1 except one neighbor of u, and we also assign u as 1, and one neighbor
Why,
of u
why assign U as 1? You can assign U as 0. No, I didn't get it. What are you saying? Come again.
no, I am saying that there is a another solution which is not which is same as this, different from this, which is implying that all half is not a unique solution in the original.
Okay, so let's.
So from on one neighbor of u we can assign half, and other one, and on u we can assign 1. So still all edges will be covered.
Yeah. Or let's. Yeah, you are. No, I didn't get it. What are you saying? That in this case, what you want to do? If it is n by 2 minus d plus half, what you want to do there? Tell me.
Yeah, then I assign u 1, and all neighbors of u 1 except one neighbor, we assign that neighbor half.
So what happens because of that?
Still all the edges will be covered, and this
What do you mean by edges are covered? How do you know there is not an edge with less than one value? You assign someone arbitrarily half here.
yeah,
It covers these edges. I agree.
yeah.
Right? But like, what about these things? How do you know they are not half? Like, how do you know that because of this you have not created a trouble? Okay. So, okay, let's see. Let's do a more careful analysis. Okay. Okay. So here is our U. Okay. Okay. We'll go there. I gradually things starts to come. Okay. And here, this is my G prime. Okay. Now here, look at the LP value, the best LP value. Okay. Let's call that X prime. Let's call that X. Let's call that, I don't know what name. Okay. X prime be the best LP solution. Okay. For this G prime. Okay. So it could assign some vertices 0, half, and 1. Am I right? Okay. So let's call that here, these guys are getting assigned, say, v equal to 1 with respect to value 1. Okay. This is going to be assigned v equal to 0 with respect to value. Yes. And this is going to be assigned v equal to half, okay, with respect to the LP value LP. Because we had several LP, so this is why I'm writing that with respect to x prime of this. Okay. Is that okay with everybody? I'm just writing it down. I have done nothing. Okay. Now I am saying to you, I want to see what is an LP of G prime. Okay. So this is, okay, let's not write. Okay. So that is the LP value of G, agreed? Minus half by getting rid of U and NU, right? You subtracted this much by half values. Okay. So half of, what is this? D plus 1. Is that okay? Okay. And plus, what is happening here? Right? So LP had assigned half to everybody. Do you agree? Like LP of G is half everywhere, every vertex, right? So now I'm trying to write LP of G prime in terms of LP of G. This is what I want. So what should I write here? Tell me what happens now. Look at V1 of x prime and V0 of x prime. What happened? How much more do I need to add? Look at V1 of x prime and look at V0 of x prime, right? These vertices are assigned how much? 0. These guys have been assigned 0, right? Because by x prime. Am I right? So they lost how much? They lost their half. G assigned them their piece of, everybody in G has been assigned half. Now V0 lost its half. Okay. So how many half did we lose? How many half did we lose?
Cardinality of V0.
Okay, excellent. So we lost half, right? And how many half did we gain? Because of V1 x prime, right?
V1.
Exactly. Excellent. Is that okay with everybody? Nothing. Is that okay?
Yes.
Okay. But this is funky. Like now you will see the magic of just writing like this. Okay. Okay. I hope I can express my, so plus half if I take, then V equal to 1 x prime, V equal to 0 x prime. Is that okay? Is this fine? I just rewrote this equation. Nothing more. I just collected half here and 1 and minus 1. Okay. Okay. Now you tell me, there's a funky thing happening. Now look at U union V equal to 0 x prime. Okay. What is this? Look at this was U, and here is some V0 x prime.
Independence.
They are independent set because all the neighbors of U are n of U, which you deleted. So if you give me any independent set of G prime, I can put U, and that's an independent set. Okay, is that fine? Excellent. But what do you know about n of U union this one? What is the cardinality of their neighborhood by our assumption?
Is V0 plus 2.
Huh?
At least cardinality of V0 plus 2.
No. So if,
At least.
or rather, we said, right, this plus 2. Look at this. I'm assuming the fact that neighborhood of I is at least mod I plus 2. Right? So I can, right? So I can write that minus cardinality of U union V0 of X prime, right? This is 2. Is that okay?
Yes.
Yes.
So are we done now? So now, what is the value of LP of Z prime? LP of G prime is equal to LP of G, right? Okay, let's see if I can, if I'm not making any mistake. Okay. Okay, so remember here. So what was this? LP of G was this minus half of D plus 1 was nothing but like half of NU, right? Right, and U, right? So I'm going to just write slightly differently. Maybe I should have done that before itself, but I'm going to write this. This, and remember, this is like half of NU plus U, right? Because those are the vertices you deleted from your graph. Okay, plus half, I'm just going to write it differently. Okay, there's nothing. Let's. This is, okay, wait. Okay, wait. I'm just not very clear with the equations. That's it. Okay. So what is neighborhood of U union V equal to 0 X prime? Can someone tell me? What is this?
Neighborhood of U union V1 in X prime. Yeah.
This is fine, right? Okay. So which implies that what we have shown now is that neighborhood of U union V equal to 0 X prime, okay, and minus U union N U union V0 X prime is greater than or equal to 2. Okay. So now what I'm saying is look at LP of G prime. This is LP of G. Let me write down what I want to say. Okay. And minus neighborhood of U. Okay. Minus neighborhood of U. I'll put it. Okay. Plus, so like I'm just adding half NU plus half NU. Okay. You get my point? I'm adding plus half NU minus half NU. Think minus NU plus half NU is minus half N of U. Is that okay? Okay. You will see why I'm doing this in a minute. Okay. Okay. And what else we had? We had the next half of, if I recall correctly, V1 X prime minus V equal to 0 X prime. Is that okay? This is exactly what we have. No, there's something else also missing, no?
Half for U.
Half.
Yes. Yeah. I also should have plus half for U. Okay. Is that fine? This is something which I was missing. You're right. But now I want to club these things. Okay. So what I want to say is that, okay, fine. Look at LP of G prime is LP of G minus N of U plus, okay, what I want to say is plus half of, you will see why I'm writing this, N of U union V0 x prime, okay, minus half, if I take common, I get U. Is it? No. This is like.
It should be minus in the previous equation.
No, that's okay, no?
Initially, it was minus half into D plus 1. So,
Yeah. So just 1 second. Look, I'm just taking from here to here. Like that D plus minus half of D plus 1, D was N of U and U was for 1.
yeah, so it's a minus half there. The last term in that LP of G prime equal to that line. It's minus half.
Oh, you mean this one?
Yes.
Oh, you're right. Okay. Okay, this is why I was having a difficulty here. Okay, so now let's look, I'm not very good with these equations, but I need to do these equations. Otherwise, I have no choice. U union is this one. It's the same thing, right? Let's see. So NU is NU here, right? Now I'm clubbing N of U with V1 of X prime. Is that okay? Half of this and half of this. And I'm clubbing minus half with minus V0 of X prime. Is that okay? But then we are done. Because what is this? LP of G minus NU. If you take half common out, what is this? What is this now? It is N of U union V1 of X prime, okay, minus U union V0 of X prime. Is that okay? And what we know about these things? What is this minus this? Is at least
2. At least 2.
Is that what we know? Right? At least 2. So I can write this as, right, minus N of U, right, plus half of 2. Is that okay? That's it. How many of you have followed this computation? If you have not followed it, okay, we will do it once more, okay? But all I wanted to tell you that if we are able to ensure that independent set has this property, then we can deal with it. That's all that I was trying to do. Then we can make progress. Okay. So LPG is at least this much. Now you can do whatever we were doing before, is that what is this? K minus LPG minus, right, K minus D minus LP of G prime, right? So this is K minus LP of G minus K minus minus plus D minus minus plus LP of G prime. Okay, so K get cancelled. Okay, and D is nothing but N of U. Okay, so what do we get now? And LP of G prime is at least, so this number is D plus LP of G prime minus LP of G. Okay, and what is the property? What is LP of G prime? Is at least this quantity is at least D plus LP of G prime is LP of G prime minus N of U plus 1, right? Minus L of P of G. So no, this is G. So this and this will get cancelled. This and this will get cancelled. And this is at least 1. Is it fine? So, I mean, this is just a simple computation, okay? But in essence, what I want to say that what is an interesting thing that if every independent set in my graph has larger size neighborhood, right? Then we are able to make some progress, okay? But what was happening to the previous algorithm? What was that previous algorithm was doing? So basically what previous algorithm was doing that for every independent set, okay, it was making sure that it's this guy, like for every independent set I, enough. So after applying reduction rule, basically what we are saying that n of I is greater than equal to I plus 1. We were not able to ensure this, that it is at least I plus 2. Okay, I'm just building up for the proper lecture, but at this point of time, all I want to tell you that these are the features. Now, you might ask yourself, what happens when I have an independent set, okay, and I have another n of I, okay, and I know that suppose n of I is less than equal to I. What is happening then? What is happening? Can anybody tell me? If we had such an independent set, what will that look like? What will that correspond to? Imagine I have something, and I have something. Say this is I, this is n of I, and this is rest. Does it remind you of something?
Ground limit?
Yes. So ground reduction is nothing but basically trying to identify, okay, this situation combinatorially. Why? Because whenever you have such a thing, then basically what happens is that if you like, then you know there is no saturating here, then you will find something big here that had a seats because of pigeonhole, because of Hall's theorem, which implies that if you look at the minimal, then they're saturating. You can use that to get a crown. Hence, you can apply reduction. And you can show that if a graph had some sort of crown, then you should have all half is not a unique solution. Right? Why? Because even the graph, suppose you had a crown. Okay, what is a crown? There exists a matching that saturates this, right? And this, right? So if you do have a crown, then I claim to you that all half is not a unique solution, because like you can show that all half is not a unique solution in those cases if you have some kind of crown. So basically detecting crown and all half are somehow, goes hand in hand in certain senses. But what I want to tell you is that imagine that if I have an independent set I here, okay, such that neighborhood of I is exactly equal to I plus 1, for example, okay, and this is a minimal such set, okay. What is this? This is an I is a minimal independent set with the property, okay, that n of I is equal to mod I plus 1. Okay, what is the meaning? That if you look at any I prime here, okay, and you look at its this, then cardinality of ni prime, okay, is strictly greater than equal to mod I plus 2. Okay, suppose such an independent set exists. Can you come up with some sort of rule for this? Okay, so suppose we have such a situation. Now, there's a funny thing happening here. Okay. Doesn't it sounds very natural that let's pick everybody else? First of all, notice there's a matching that saturates I. Can someone prove this to me? That there exists a matching that saturates I. For every neighborhood, what is this? It's larger than that I prime, right? So by Hall's theorem, what do we know? There exists a matching that saturates I, not an I. Man. Now, is it not tempting in this case? So, for example, what is crown rule? Crown rule tells you that suppose I would have been equal to n of I and there's a matching saturating that. What does crown rule tells you? Hey, then take all of n of I and you are done. That's a good reduction rule, right? What was crown rule? Suppose I is equal to n of I and we had a matching that saturates this, then what can I say? Do you remember the crown rule? Then you pick up n of I in your solution, you are done. But now I cannot say this because it is n of I is like n of I is mod I plus 1. Right? And there's a matching that saturates I. I cannot say this anymore. But what you know, any optimum solution picks at least one vertex from each of these guys. Do you agree? Okay. And now further assume that there's an edge here in this. What can you say then?
One of its endpoint must be in solution.
Yeah, that's okay. Then I want to claim that you better pick all n of I.
But can we even have such an edge?
Why not? Suppose, I mean, look, it's just a part of the graph, piece of the graph, I is independent set, and n of I is just some subset of vertices. And I'm saying, suppose there is an edge. Okay? Then we will be able to show to you that there exists an optimal solution that contains all of this. Okay. So that's kind of reduction rule. And so what we will try to do in that case, that okay, fine. So what is our goal to make progress? Our goal is to understand what happens to those independent sets whose neighborhood is up to I+1. We want to apply some reduction rule to pre-process those things, okay? And ensure that my graph has a property that every independent set has size at least, like neighborhood of every independent set size is at least 2 more than the size of independent set itself. Okay, so what I'm trying to mimic, if you recall correctly, what was degree 2 reduction rule? What was degree 2 reduction rule? What is this degree 2 reduction rule? Is it not that situation? It's exactly the same situation. No? There is an independent set I, n of I is I+1. So I'm trying to generalize this reduction rule to make that sure that this degree 2 vertex is like a set of independent sets and its neighborhood. So what was our reduction rule if I recall correctly? If there's an edge between them, what was the reduction rule? We picked up both vertices in our solution. Is that right?
Yes.
Okay. Because I need to pick up that much. Okay. 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 But if you recall correctly, if it was an independent set, then we did what we call folding. Okay. Remember, we deleted these 2 vertices, put 1 vertex and do this. Okay. So our new reduction rule is going to happen is as follows. Okay. It's exactly the same thing. Suppose we have I, and this is n of I+1. Like n of I is exactly equal to I+1. Then we will be able to show that if there is an edge here, okay, then there is an optimal solution containing n of I. Okay, this is a point. Okay, so do you see why? It's a bit of funkiness, but like suppose you pick up some vertices from here and you pick up some vertices from here, right? Any optimum vertex cover will do this job. Am I right? Okay. So, and you know that how much will you pick? You will at least pick as many as I vertices from here. You have to pick these many vertices because there was a matching that saturated this. Okay. Now, these are the vertices which you did not pick. Am I right? These are the vertices you did not pick. You have to pick all its neighbors, no? Do you agree to that? You have to pick all its neighbors. Okay. So, how many vertices did you pick? If you picked up these vertices, how many guys did you pick? If this size is some A, and suppose this guy's size is say A+1. And this is a property that every set here has say at least that many neighbors. So how many vertices did you pick from here? A+1? Okay. Now, how many vertices did you pick from here?
I minus A.
Alternative 5 minus A.
Okay. So how many vertices did you pick?
I+1.
Then you better pick the remaining one, no? Right? Is that okay? You understand or not?
Yes.
Okay. So the and you know that because there is an edge here, you will pick some vertex from here because there's an edge here. Right? So this is how we will play with surplus. That look, boss, if you did not pick something, then you have to pick lot many vertices from here because their neighborhood is larger than this. Okay, but the remaining guys okay, so you did not pick this, you have to pick all his neighbors, and then you picked up some vertices from the top, right? You have picked up, so you at least picked up these many vertices from this side and this side. Then why not move all these guys to its neighborhood itself, because it has a possibility of picking more than what just these I guys could pick up. You understand my point? Okay. So we will play with these kind of reduction rules. Okay. And our objective will be, is that I will explain to you much more and much more cleanly. Okay. So what is my objective? My objective is, okay, to apply reduction rules to ensure that in resulting G, for every independent set I, what is the property? Size of neighborhood of I is greater than equal to mod I plus 2. Okay. So I will have several properties, several features of this. First will be this. Second, and all half is the unique solution. Okay. And when we will branch, we will have this two property that, oh, all half is the unique solution and every independent set has large expansion, like at least plus 2 additional expansion. We will use this two property to say, then the LP drops in one side at least by half, but in other side, it will drop by 1. So half comma 1 will give us good branching rule. Okay. And this terminology, this has a very nice combinatorial terminology already proved by Lovas in 50s or 60s or 70s. But if you look at the Lovas Plummer book of matching theory, okay, he defines this word as surplus. Okay. So what is a surplus of a graph? So this is a very beautiful, let me at least define the terminology and then we'll stop for the day. Surplus. So what is the surplus of the graph? Okay, so this is what is defined. Okay. So surplus of some set X, okay, is basically is this. So surplus could be independent set. Okay. And surplus of A, where A is family of independent set, is basically is equal to min over, okay, X in this set A. And what is this? Okay. And what is a surplus of a graph? Surplus of G is defined to be minimum, okay, surplus over all independent sets in G. Okay. So it will be fun if you go and check this terminology on this. So what is a surplus of a graph? You look at every independent set and look at what its neighborhood. Among all this, choose the one for which n of x minus x is the minimum quantity, right? So notice if I had independent set and like this, what is surplus of this graph? So surplus of this graph is what? It is 1 minus 3, it is minus 2. Because it is for this set, it is n of x minus kernel t. So surplus of a graph could be a negative quantity. Because what is surplus? Surplus of a set is size of its neighborhood minus its kernel t. And what is the surplus of graph? you take this over all independent sets in my graph. Okay. So what we are going to ensure by our reduction rule, the surplus of my graph is at least 2. It's neither negative nor 0 nor 1, but it is at least 2. If the graph has surplus anything less, we will find an opportunity to apply reduction rules. Okay, is that fine? Okay, so that's the overall goal. So maybe the way at least I wanted to re-backtrace, but that didn't happen in a nice way. Okay, so we'll do it from the forward way and see how it goes. Okay, okay. So that's all that I wanted to tell you today. So we saw one algorithm cleanly, and we'll try to see another algorithm cleanly using this in the next class. Okay. Okay.